In this class, we will study differential amplifier, but this time we will focus on the mismatch between the transistor and resistor and its adverse consequence on the differential DC output. So that differential DC output that exists in real life differential amplifier because of the inevitable mismatch between RD and MOS is characterized by a parameter called input offset voltage. So here we have a differential amplifier where the two resistors, they are distinct, RD1, RD2. Similarly, two MOS, they are also distinct. Mismatch is very small, but it exists. So in this scenario, suppose we give the same DC to both the MOS gate. In that case, what turns out is that the output DC that we see, they are not equal. And this happens because of the mismatch in these two quantities. And MOS mismatch, this implies that their threshold voltages, they are not same. Similarly, their aspect ratio, that means ratio of width to length of the channel, that is also not same for the two MOS. So this is the meaning of distinction between these two. We will assume that COX for both the MOS, they are same. And mu n is of course going to be same because both are of n type. So what happens that if we have these mismatches, then the output voltages, they are not going to be same. And we can see that why that will happen, because we know that this drain current ID, so this ID we know that is given by 1 by 2 mu n COX W by L VGS minus VTH whole square. Of course, we are talking about the scenario in saturation because we always use MOS in saturation. So here you can see that even when we are giving the same gate voltage, their source is anyway common. So gate to source voltage is going to be same for both the MOS. So despite that, because of the difference in the threshold voltage and the aspect ratio, their drain currents, they are not going to be identical. So both the MOS, they will have different drain currents, ID1 and ID2, right? So because of that, now we can calculate what will be the respective output DC voltages. So let me emphasize that this analysis of input offset voltage is for the DC quantity. In today's discussion, there will be no time varying quantities involved. So because of this ID, we know that VO plus DC will be produced, which will be equal to VDD minus R1 ID1. Similarly, the other DC will be VDD minus RD2 into ID2. Now here you can see that because ID1, ID2 they are different, RD1, RD2 they are different. So these two voltages they are also going to be different. So that means there will be net DC at the output given by this expression, and this will be equal to minus RD1 ID1 minus RD2 ID2. So ideally this DC offset should be 0, but this will not happen in real life. So now we are going to estimate that what should be the additional DC we should supply at the input so that the DC offset is equal to 0. So the input DC offset voltage is equal to input voltage, which of course is going to be DC, such that the output offset voltage, which is VO, is equal to 0. So this is how we are going to set up the equation and find out the input DC offset voltage. And if you see any op-amp, the data sheet of op-amp, then this will always be one of the characteristic parameter mentioned in the data sheet. And at the end of this class, we will see example of LM741. Although it is based on BJT, not based on MOS, but even the BJT differential amplifier, they suffer the same issue. So now our objective is to find out what should be the additional gate to gate voltage, the input voltage, so that the output DC is 0. So now what we are going to do, we are going to apply different gate DC voltages, and keep in mind this phenomena is present even when this tail current source is ideal. Right? So now we are going to give, say, VG1 here to the MOS1 and VG2 to the MOS2, and then try to find out what is the difference between these two voltages so that this output voltage is 0. So here we will have to set up equation. So we have VG here between ground and gate, VG2 between gate and ground, and then there will be net gate to source voltage, VGS1 here and VGS2 here. Right. So here we can find VG1 minus VG2 equal to VG1 minus VS minus VG2 minus VS, because source is common to both the MOS. Right. So this implies VG1 minus VG2, which we will call as input offset voltage, is equal to VGS1 minus VGS2. And now we can use this equation to convert VGS into ID, right? Because it is this equation which is used to define the condition for input out offset voltage. That means when this quantity is 0, so we will convert gate to source voltage into the form of drain current, and then ultimately find out this quantity in terms of device parameter, the mismatch between resistors and mismatch between threshold voltage and W by L of MOS. So that is our objective. So we can substitute each of these gate to source voltage in terms of the current. So we know that this is going to be equal to VTH1 plus 2 ID1 divided by mu m COX W by L and whole square root. So this is for VGS1. Similarly, for VGS2, we have VTH2 plus 2 ID2 divided by mu m COX W by L. And these aspect ratio, they can be distinct for these two MOS. So that is why we are designating them by subscript 1 and 2. And COX is assumed to be constant. So we can now write a difference of VTH delta TH, and we can put a constant for this. So this becomes 2 ID1 by, let us say, K dash W by L1 minus 2 ID2 divided by K dash W by L for the second MOS here. So as I mentioned, our objective is to find out the expression in terms of differences in aspect ratio and differences in RD. And RD is related with drain current. So we are now going to write these drain current and aspect ratio as function of their average value and their difference value. So for that, we are going to use this notation. This ID1 can be written as ID1 by 2 plus ID1 by 2. That is understandable and trivial. Similarly, ID2 also as ID2 by 2 plus ID2 by 2. So we want these currents as function of their average value and the difference values. So now we can here add ID2, half of the other current, and subtract ID2 from the second term. So it remains same. Similarly, here also we can add ID1 by 2 and subtract ID1 by 2. So here you can see that these currents now can be written as average of the two currents plus difference of two currents. So similarly, ID2 can also be written as, we will be calling this as ID. This is the average. This term is common to both. And this becomes delta ID by 2. So here ID is average of the two currents and delta ID is difference. Right. So here we can see that this is ID ID1 is ID plus delta ID by 2, and ID2 is ID minus delta ID by 2. And here these two terms, they are also called common signal, and these as differential signal. So this way of representing two quantities, this is also called as uh, common mode signal representation plus differential mode signal representation. So we are going to substitute all the drain currents, all the resistors, all the W by L ratio using this notation in this equation 2 that we obtained. So here we are going to substitute ID1, ID2, W by L1, W by L2 using that common mode and differential mode representation. So we wanted to know that how much mismatch in these quantity leads to the this VIO, the input DC offset. So here you can see that VIO is now delta VTH plus 2 ID1 can be written as ID plus delta ID by 2. In denominator we have K dash, W by L1, which will be W by L plus delta W by L by 2. So this is first term. Then we have to write the second term, which is 2 ID minus now delta ID by 2 divided by K dash W by L minus delta W by L by 2. So this is what we obtain after substituting the average and difference of the two quantities ID and W by L. Now here we can see that 2 is common to both the terms, K dash is common to both the terms, ID is common to both the terms, W by L is common to both the terms. So all these four terms can be taken outside, and when we do that, this will get divided by ID. Similarly, this delta W by L will get divided by W by L in both the terms. So when we do that, we get 2 ID by K dash W by L whole square root into, now this will be 1 minus delta ID by 2 ID. Similarly, in the denominator, 1, this will be plus delta W by L by 2 W by L. So this is the first term. Similarly, the second term will be 1 minus delta ID by 2 ID whole square root 1 minus delta W by L by 2 W by L whole square. So now we will do the approximation. So there will be two approximation involved. So first approximation that we are going to do is using this formula, that is 1 plus x raised power plus minus 1 by 2 is approximately equal to 1 plus minus 1 by 2x, for x very small compared with 1. So using this approximation, we are going to approximate each of the four factors that we see on the right hand side in the square bracket. So first we will simplify this term, then this term. So this will become 1 plus x raised power minus 1 by 2, right? So what we will get is delta VTH plus 2ID K dash W by L whole square into 1 plus delta ID by 4 ID into 1 minus delta W by L by 4 W by L. So these two terms, they arise because of the first term, this one, these two. Similarly, for this ratio, we get a product of two terms, that is 1 minus delta ID by 4 ID into 1 plus delta W by L 4 W by L. So this is after first approximation. So ideally we should write it like this. This is the first approximation. Now we will have to multiply the two factors appearing in both the terms. So we get equality now, delta VTH plus 2ID by K dash W by L 1 by 2 into, so when we multiply these we will get four terms. So first is going to be 1, second is going to be this ratio itself, it is plus delta ID by 4 ID, then second term is going to be this one minus delta W by L divided by 4 W by L, and there will be a fourth term which will be product of this one and this one. So that is going to be minus delta ID delta W by L divided by 16 ID W by L. So these are the four terms from the product of first one. Similarly, there will be four terms arising because of the product of the first one, second one, that means this one and this one. Four ID and plus delta W by L 4 W by L, then minus delta ID delta W by L divided by 16 ID W by L. So out of these, we see that this term and this one will get cancelled out. Similarly, this second order term will also get cancelled out. So what will be left here is delta VTH plus delta ID by 2 ID minus delta W by L by 2 W by L. And of course, there will be this constant. So here we see that we have the input offset voltage in terms of the difference in the aspect ratio and difference in the threshold voltage, but now we have difference in terms of the difference of the drain current. So this we want to represent as function of the RD and its difference, because this is another location where the differential amplifier, uh, two halves of the differential amplifier become distinct because of the mismatch in the RD in addition to W by L or threshold voltage. So now we have to find how to substitute this in terms of RD. So for that, we will take the help of the condition which should get satisfied uh, when we supply input offset voltage. So when we apply the input offset voltage, what will happen is output DC offset is going to be 0. That means this quantity is going to be equal to 0. So we are going to take the help of that equation to get rid of this one. So for 0 output DC offset, what will happen is RD1 ID1 equal to RD2 ID2. Now these two, they can also be written in terms of their common and differential values. RD plus delta RD by 2 ID plus delta ID by 2 is equal to RD minus delta RD by 2 into ID minus delta ID by 2. Okay. Right. So here when we expand this, we get RD plus RD delta ID by 2 plus delta RD by 2 ID plus delta RD by 2 delta ID by 2 equal to RD ID minus delta RD by 2 ID and then minus delta ID by 2 RD plus delta RD by 2 delta ID by 2. here. So here we see that these two, they will cancel out. What we will have is RD delta ID is equal to minus delta RD ID. So this is delta ID by ID is equal to minus delta RD by RD. So now we can use this one, the 5 into here, this fourth one. So the fourth one will become VIO is equal to delta VTH plus 2ID by K dash W by L square root into minus delta RD by RD minus delta W by L by W by L. Yeah. So even this can be replaced in form of gate to source voltage using the fundamental equation of the drain current and gate to source voltage. So VIO, the input offset voltage that we will have to apply, is VTH plus, this will turn out to be VGS minus VTH. So these GS and TH, they are the averages value of the two different values that we have to apply. So here minus can be taken this side common. So this become delta RD by RD plus delta W by L by W by L. So this is the additional input voltage, mismatch in the input voltage that must exist at the input so that the output offset is 0. This quantity is going to be very small. This will be typically of nanovolt or in the base case microvolt. But keep in mind that this will get amplified, and on the output side, the usual offset that you will see will be significantly larger compared with the input. So although on the input side, this quantity is very small, its effect on the output side will be non-negligible usually. So one has to take care of this in some of the scenarios. So here in the MOS, what happens is that the gate is open circuit. So this impedance looking into gate R, G or Ri is infinite. So there will be only, there will be no current Ig is equal to 0. But if someone implement the same differential configuration with the BJT, then there will be not only the mismatch in the base voltage, but there will be mismatch in the base current that flows into the BJT. So we are now going to quickly see the scenario with respect to BJT differential amplifier and try to find out the input offset voltage for BJT. So for BJT also, one has to apply distinct base voltage so that the VO is equal to 0. So here when VO is equal to 0, we know that equation that will be valid is RC1 IC1 equal to RC2 IC2. That minus will be there, because when you find out the net output voltage, that will be actually difference of these two. This minus will not be there. So here also, to find out the input offset voltage, we have to take the difference of these two voltages, and they can be written in terms of base to emitter. Emitter is common to both. And we know that for a BJT, this collector current IC and base to emitter, they are related as IC is equal to IS e raised power minus VE divided by VT. So here transistor will be characterized by this VT and IS. So using this, we can rewrite the input offset voltage as ln this minus can be taken here. And we know that so to keep the thing simple, we will take the same threshold voltage for both the transistors. So this becomes VT ln here. And for output DC offset equal to 0, that implies RC1 IC1 is equal to RC2 IC2, which says IC1 by IC2 is equal to RC2 by RC1. So this voltage now becomes VT ln RC2 by RC1 into IS2 by IS1, right? And these quantities we again represent in form of the common mode quantity and the differential quantity. That means RC minus delta RC by 2, RC plus delta RC by 2. Similarly, IS minus delta IS by 2 divided by IS plus delta IS by 2. So now we will do the approximation and convert everything in the form of numerator quantities only. So we have, and here you can see that RC can be taken common, IS can be taken common. So we will have 1 minus delta RC by 2 RC, and this is where we will do the approximation. This we will take in the numerator and substitute by 1 minus delta RC by 2 RC. So this is approximation, because here we are using 1 plus x raised power minus 1 is approximately 1 minus x. So this is what we have done for the second term. Into for IS we have similar scenario. So here you can see that both the terms, they are turning out to be same. Similarly for this IS also we will get the same situation, delta IS by 2 IS whole square. So now we can expand these and neglect the second order term in delta. So we are going to get the second approximation, that is VT ln, we are going to get is 1 minus delta RC by 2 RC and 2 here. The second term we are going to neglect. So that is why we will have this, and similarly for the IS term. And this 2 will get cancelled out, this 2. So similarly for IS also we will have delta IS by IS. So now here we have 2 log terms, 1 minus delta RC by RC plus log 1 minus delta IS by IS. Now we know that log 1 plus x is approximately equal to x, for x very small compared with 1. So we do another approximation and get VT 1 minus delta RC by RC. Here no, this term will not be there. We will have only minus RC. Similarly here minus delta IS by IS. So V offset is minus VT delta RC by RC plus delta IS by IS. So this is the offset voltage required for BJT. But as I pointed out, for BJT, there will be base current also. There will be some base current flowing through this. So one can find out what is the mismatch in the base current that exists. So base current delta IB is going to be IB1 minus IB2, and we know that this is equal to IC1 by beta 1. Similarly, this is going to be IC2 by beta 2, because we know that IC by IB is equal to beta for a BJT in active region. So that is where we are talking about all these things. So here also once again IC plus delta IC by 2, similarly beta plus delta beta by 2 minus IC minus delta IC by 2 and beta minus delta beta by 2. So here IC by beta can be taken common because this is there in both the terms, and then one will have 1 plus delta IC by 2 IC divided by 1 plus delta beta by 2 beta minus 1 minus delta IC by 2 IC 1 minus delta beta by 2 beta. So here denominator term can be taken into numerator and approximated using this formula 1 plus x minus 1 approximated to x. So when we do this, we get IC by beta 1 plus delta IC by 2 IC into 1 minus delta beta by 2 beta minus 1 minus delta IC by 2 IC and 1 plus delta beta by 2 beta. Yeah. So here one can expand these terms, and what one will get is the first order term, zeroth order term, that means these 1 1 they will get cancelled out, and the second order term delta IC into delta beta they will get cancelled out, and what we will have is delta IC by IC minus delta beta by beta here. So this is input offset current, and at this for this case we have already seen that IC1 RC1 is equal to IC2 RC2. There will be no DC offset, and this is similar to what we got for the MOS case, and this will translate to delta IC by IC is equal to minus delta RC by RC. So using this formula, we can substitute this term and we will get input offset current equal to IC by beta minus delta RC by RC minus delta beta by beta. So we now have these quantities in terms of the mismatched parameters of the differential amplifier. Mismatch for transistor and mismatch for the load resistor. Now we can look at the example of LM741 data sheet. So here is the data sheet for LM741, and here we can see that we have input offset voltage, and this voltage is very small. You can say that 1 millivolt typical, and maximum will be 5 millivolt. But keep in mind that there will be gain, so on the output side its effect will be significant. Similarly, the input offset current is from 200 nanoampere to 20 nanoampere to 200 nanoampere. Maximum is 200 nanoampere and typical value is 20 nanoampere. So during the lecture I mentioned that this voltage is of order of nanovolts or microvolt, but actually it is of order of millivolt. So in some of the scenarios, what we will have to do that we will have to apply our input like this. This is a sinusoidal input that we want to get amplified. In addition to that, there might be certain small DC that we will have to apply, say VIO, to one of the MOS to get no DC at the output. So this might be the scenario of using MOS incorrect way to get rid of the DC output that we get here.